There are two different general types of waves. There are transverse waves and longitudinal waves. All types of waves will transfer energy without transferring the matter. So the particles of matter, if there is a medium, are going to be vibrating, but going back and forth, not going from one location to another. In the case of a transverse wave, the direction of the particle motion is perpendicular to the direction of the wave motion. The wave in this case is transferring from left to right, but the particles are going up and down. This is like taking a spring and shaking it up and down. A longitudinal wave, the particles are moving parallel to the direction that the wave is moving. So in this case, the particles are vibrating back and forth, left and right, and the wave is transferring from the left to the right. So the energy is going from left to right, but the particles are vibrating back and forth around a fixed point. But the particles are moving parallel to the direction that the wave is traveling. With a transverse wave, there are several different parts of this wave that you need to be able to identify. The black dotted line here represents the equilibrium position, which is where that rope or whatever your medium is would be if the wave was not passing through it. The amplitude of a wave is defined as the maximum displacement from equilibrium. So from that dotted line where it would be without the wave to the highest point, or from where it would be without the wave to the lowest point, would be the amplitude of the wave. The highest point is called a crest. The lowest point is called a trough. Now, which is high versus low is a little bit arbitrary, but those are both positions of maximum displacement, just in opposite directions. The wavelength of a wave would be from crest to crest, or trough to trough, or any other distance that's equal to that, like equilibrium position, but not to the very next adjacent equilibrium position, but to one after that, where we've gone through an entire wave cycle. The wavelength is abbreviated with the Greek letter lambda. So you might want to pull out your table of units and add that in there. Wavelength is abbreviated with the lambda. It is measured in meters. It is a length. So we'd measure it just like any other length. But that distance in wavelength from crest to crest, from trough to trough, anywhere along that wave where the particles are doing essentially the same thing would be one wavelength apart. These particles that are one wavelength apart, or these positions in the wave that are one wavelength apart, are said to be in phase. They're doing the same thing. So this point would be in phase with that point. They're both kind of in the same location on the wave. Now, when you're asked what direction the particle is going to move, it's important that you pay attention to what direction the wave is traveling. So, for example, if this wave is traveling from left to right, and we're asked what is happening to the particle right here, well, we think left to right, oh, it's going up. But what you need to remember is that it's the wave that's moving, which means what was here in terms of the wave is now going to be over here. So this particle would actually be moving downward as the wave passes through, whereas a point over here would be moving up as that crest is about to come. So when it comes to things being in phase, this particle right here is about to move up as the crest comes through. This part is about to move down as the trough comes through. So even though they're both at the equilibrium position, they're not doing the same thing. So they are not in phase. This point over here is about to move up as a crest comes. So it would be in phase with this point here. So an example of a transverse wave would be light or anything on the electromagnetic spectrum. Now, the electromagnetic spectrum, they are transverse waves. They are waves that do not require a medium, though. These are the only waves that are able to travel through empty space. For light, when you're looking at the different parts of the wavelength, or more specifically the frequency, which would be related to a wavelength for an individual wave, will correspond to the color. So the frequency or the wavelength of the light that you're seeing tells you what color the light is. The amplitude corresponds to the brightness of the light. So a higher amplitude wave of the same frequency would be a brighter light of that same color. Next, we've got the longitudinal waves. Longitudinal waves, instead of having crests and troughs, have what are called compressions and rarefactions. So compressions are where the particles are compressed together. Rarefactions are where they're spread apart farther than they would be at equilibrium. So this is like a spring taking it and pushing and pulling it. Those particles are moving parallel to the direction that the wave is going. There's places where they're bunched together and there's places where they're stretched apart. The distance from a compression to a compression, or a rarefaction to a rarefaction, would be the wavelength of that wave, or anything else that's in phase. It's just a little harder to see it with the longitudinal wave. Longitudinal waves do also have amplitude, having to do with the maximum displacement from the equilibrium. But again, it's not something that we can see quite as easily on a diagram of a longitudinal wave. An example of a longitudinal wave would be sound. So when you talk or make any type of noise, something is vibrating, and that vibration is causing compressions and rarefactions within the air or whatever medium your wave is traveling through. And then your eardrum detects that wave, and stuff happens in your brain that transfers it into a sound. For sound, the wavelength or the frequency would correspond to the pitch. So a very high frequency is a high-pitched note. A low frequency is a low-pitched note. The amplitude corresponds to the loudness of your sound. The last thing that we need to talk about right now, a little bit more, is that whole in phase, out of phase thing. Waves are said to be in phase if they have the peak, the crest, and the trough are lining up, the equilibriums are lining up. Or if it's longitudinal, if the compressions and rarefactions are lining up and happening at the same time. So for this red and black wave for number 1, we've got equilibrium, they both go up, they peak at the same time, not necessarily the same height, but the same time, back to equilibrium, trough at the same time, back to equilibrium. They're doing the same thing at the same time. 180 degrees out of phase means they are doing the exact opposite of the other one. If you think about your sine and cosine graphs, it takes 360 degrees to make one complete cycle. So being 180 degrees out of phase, that's half of a complete cycle. So you're doing exactly the opposite thing. They're both at equilibrium at the same place, but when one is at a crest, the other is at a trough. So that would be 180 degrees out of phase. 90 degrees out of phase means essentially you're shifting that graph from where it would be if it was in phase, shifting it 90 degrees, or pi over 2 in terms of what we usually do for graphs of sine and cosine. So not exactly out, but kind of halfway in between, and being completely in phase and completely out of phase. So when one's at equilibrium, the other's at either a crest or a trough. When one's at equilibrium, the other's at a crest or a trough, would be 90 degrees out of phase.